Welcome back, everyone. So, in part one, we really covered the basics of vectors. But today we put all that knowledge to work. We're going to go from the what to the how and turn that abstract theory into a seriously powerful tool for solving real geometric proofs and, yeah, acing those exam questions. Let's just jump right in. Okay, so let's kick things off with a question. Imagine you're trying to tell a satellite where to point its thrusters, or maybe a character in a video game which way to move. You don't always care how far it needs to go, right? But you absolutely 100% need to know which way to point. So how do you do that? How do you capture just the direction and completely strip away the distance? Well, that is the exact problem the unit vector was made to solve. And here it is, our answer. A unit vector is, well, it's basically a standardized pointer. You take any vector you want and you scale it down so its length is exactly 1. Think of it like a compass needle. Its only job is to point. It doesn't tell you how many miles to go, just which direction you should be facing. Okay, so how do we actually make one of these unit vectors? It's actually a really slick 3-step process. Let's take the vector 3, 4. First things first, we need to know its current length, its magnitude. For that, we just pull out the good old Pythagorean theorem, the square root of 3 squared plus 4 squared. Gives us a length of 5. Now, here's the magic. To get its length down to 1, we just divide each of its parts by its current length. We're literally shrinking it down to size. And that leaves us with our unit vector, 3/5, 4/5. It's pointing in the exact same direction, but now its magnitude is precisely 1. Simple as that. All right, we've got the how-to down. Now for the fun part, let's actually apply it. We're about to see how this one simple idea can be used to elegantly solve some classic geometry problems you'd find in any textbook. So we are diving right into exercise 8A. Now, these problems are designed to get us thinking spatially, proving geometric rules, navigating 3D shapes. This is really where vectors stop being just numbers on a page and become a real tool for thinking and for reasoning. First up, we've got question 4. So, picture this. We have a triangle, ABC. Simple enough. But then we're told that points X and Y are the exact midpoints of 2 of its sides. Our job? Use vectors to prove something you might actually remember from geometry class, that the line connecting these midpoints, XY, is perfectly parallel to the triangle's base, BC. And what I absolutely love about this is just how cleanly the vector math cuts right through the problem. To get the vector for xy, we just calculate y minus x, which boils down to b minus a. Now for the base, bc, we do the same thing. And because x and y are midpoints, it simplifies to exactly 2 times b minus a. And this right here, this is the whole thing. Because vector bc is just a scalar, the number 2, times vector xy, they have to be parallel. It's just a beautiful, airtight proof. All right, let's keep the momentum going. Question 5 takes us into 3 dimensions with a cuboid, asking us to find vectors to a midpoint and a point on an edge. Then, question 6 throws a regular octagon at us, asking for vector expressions and a scalar relationship. It just shows how versatile vectors are, no matter the shape. And boom, here are the solutions. For the cuboid, the real trick was just setting up a coordinate system at a corner and then finding the coordinates for m and n. For the octagon, it was more about path finding, like adding and subtracting the vectors we knew to find new paths like BC and EF. And that final relationship for S, that comes straight from the specific geometry of a regular octagon. Now for our final textbook challenge, a real classic proof. We need to show that if the diagonals of any quadrilateral cut each other exactly in half, then that shape has to be a parallelogram. This is just a fantastic example of using vector algebra to prove a fundamental rule of geometry. So the entire proof hinges on one simple idea. If the diagonals bisect each other, it means they share the exact same midpoint. That gives us our starting equation. From there, it's just algebra. If we rearrange that equation one way, we discover that the vector AB is identical to the vector DC. Not just parallel, I mean identical in length and direction. Then, if we rearrange that same starting equation a different way, we prove that vector AD is identical to vector BC. And if both pairs of opposite sides are identical vectors, well, it has to be a parallelogram. It's just so elegant. Okay, we've worked through the textbook theory, we've done the application. Now let's sharpen those skills for where it really counts. It is time to tackle some exam-style questions.
Here we go, a classic exam question. It asks for the unit vector, but you gotta notice the twist. It has to be in the opposite direction of the vector 5, -12. This is a perfect example of a little detail they throw in just to make sure you're reading the question carefully.
So the solution is really a two-step process. First, we do what we already know how to do, find the unit vector pointing in the same direction. The magnitude of 5, -12 is 13, which gives us 5 over 13, -12 over 13. Now for that crucial second step. How do you get a vector to point the other way? Simple. You just multiply it by -1. All that does is flip the sign of each component, giving us our final answer.
Let's try one more. Find the unit vector for e equals -3, -4. But look at that second part of the question and verify it. Now, this isn't just an extra chore they're giving you. It's the examiner's way of giving you a chance to catch your own mistakes before they do.
So how do you verify it? You take the unit vector you just calculated, in this case, -3/5, -4/5, and you find its magnitude. You run it right back through the Pythagorean formula. And if you've done everything correctly, the fractions will always work out perfectly to the square root of 1, which is, of course, 1. This confirms your answer has the one defining property of a unit vector. Its length is 1. It's a fantastic way to double-check your own work when you're under pressure.
So there you have it. From the simple definitions to geometric proofs, all the way to exam questions, we've seen that vectors are this incredibly powerful tool. I mean, they can be used to prove ancient theorems and to guide modern spacecraft. The only question left is, what kind of problems are you going to solve with them?